Hello, welcome to CS with Terry. Today we will talk about merge sort. Compared to selection, bubble, and insertion sort introduced in the last video, merge sort is much more efficient. The basic idea of merge sort is divide and conquer. The idea is dividing the original problem into smaller subproblems, solving those subproblems, and combining the solutions to the subproblems to establish the solution of the original problem. Talking about it might seem a bit abstract. Let's look at a concrete example. Here we have an array with length 8. To sort this array, we can divide it into two arrays with length 4. Then, suppose there is a magical algorithm that can sort the two subarrays respectively. We just need to merge the two sorted subarrays into one sorted array. The original array will have been sorted. This approach seems simple, but you might ask, but how do I sort the two arrays with length 4? We can see that sorting the two subarrays are similar problems as sorting the original array. Thus, we can use the same approach. We can split each of the arrays with length 4 into two subarrays with length 2. Sort each of them and then merge the sorted results. Then we will have sorted the two arrays with length 4. We can repeat this recursively. To sort the arrays with length 2, we need to divide each of them into two subarrays with length 1. Arrays with length 1 are already sorted, so we can directly merge them. For all the other subarrays, we apply the same procedure, and we would have sorted the entire array. This is merge sort. It cleverly employs the divide and conquer strategy, which divides the original problem into several similar but smaller subproblems, solves the subproblems recursively, and combines the solution to the subproblems to get the solution to the original problem. With all that said, we still have a problem. How do we merge the two sorted arrays? This is actually a pretty easy problem. Suppose we have two decks of cards on the table, and each of them has already been sorted. To merge the two decks, we can draw the smaller card from the top of each deck and keep it in hand. If we keep repeating this operation, the two sorted decks of cards would have been combined into one sorted deck. Now, let's take a look at the pseudocode of merge sort. First, we design the function merge sort, which sorts the elements in array A in the left closed right open interval between L and R. At the beginning of the function, we first check whether the number of elements to be sorted is smaller than 1, which means R minus L is less than or equal to 1. If it is, then the function can return without sorting anything. Then, we calculate the element in the middle of L and R, denoted as M, which is equal to L plus R divided by 2 and then round down. We then call the function recursively to sort the elements in the left closed right open interval between L and M, and the elements in the interval between M and R. Finally, we can call the merge function to combine the two sorted arrays into one. Let's take a look at the merge function. Assuming the subarrays of A in intervals between L and M, and between M and R, are already sorted, the merge function combines them. Firstly, we make a copy of the subarray in L and M, call it capital L. Make a copy of the subarray in M and R, call it capital R. We insert positive infinity at the end of both capital L and capital R. We call the positive infinities sentinels. They can make sure that when we reach the end of one subarray, we can continue reading the other one. We let I equal to 0, j equal to 0, and k equal to L. They represent the index of element being traversed in capital L, capital R, and A. Then we enter the loop. If Li is smaller than Rj, we let Ak equal to Li. Otherwise, let Ak equal to Rj. We keep doing this until k is equal to r, and then exit the loop. At this time, we have successfully combined two sorted arrays into one. Next, we will analyze the time and space complexity of merge sort. First, let's take a look at the time complexity of the merge function. It's easy to see that it is proportional to the number of elements it needs to process. Namely, its time complexity is O r minus L. Let's then take a look at the time complexity of merge sort. For easier analysis, let's revisit the recursion tree and pay attention to each layer. Let's look at the first layer. In order to sort the array with length n, we have three operations in merge sort. They are sum preprocessing, calling the recursive function, and combine. The preprocessing is O1, we can just ignore it. Calling the recursive function is the recursion step. We can analyze it in the next layer. This means that in this layer, we only count the complexity of the merge operation. Its complexity is On because we need to iterate n times. Now, let's analyze the second layer. In the second layer, we need to process two subarrays with length n over 2. For each of the subarrays, we will also sort them recursively first, and then merge them together. Similarly, we will defer the complexity of the recursive operation to the next layer, and only look at the complexity of the merge operation in this layer. We can see that processing both subarrays takes n over 2 iterations. So, the second layer requires n iterations in total, and its time complexity is On. Similarly, in the third layer, we need to process 4 subarrays with length n over 4. Each subarray requires n over 4 iterations to merge, which comes to a total of n iterations. So the time complexity of the third layer is On. Further analysis will show that whichever layer we are at, they all require On time complexity to finish merging. In other words, the time complexity of merge sort is On multiplies the number of layers. How many layers of recursions do we need? Each time we enter the next layer, we can shorten the length of the arrays by half. So we need around log n layers to get to arrays with length 1. In conclusion, the time complexity of merge sort is On log n. The space complexity of merge sort is On. That's because during the merge operation, we need On extra memory space. After going through the algorithm, now let's visit a typical application of merge sort, sorting a linked list. As we know, the most prominent drawback of a linked list is that you cannot access its elements randomly. For example, if we want to access the 7th element in this linked list, we can only traverse the list starting from the head node until we reach the 7th element. This operation is very slow. Because elements in linked lists can only be accessed sequentially, we need to pay special attention when sorting them. Merge sort is particularly suitable for sorting linked lists, because its key operation is merging two sequences, which happens to be sequential. Specifically, to sort this linked list of length 8, we should divide it into two sublists with length 4 and sort them respectively. Then, we only need to merge the two sorted lists. Since merging is a linear operation, it's easy to implement. If we repeat this recursively, the linked list will be sorted. By the way, the space complexity of merge sorting linked lists is O1. It means we don't need any extra space. Excellent! That's all for merge sort. Before we end this video, let's think about the following problem. Suppose there is a 1 TB file in the disk. The file is full of integers with format int64. When we only have 8 GB of memory, how do we sort the numbers in the 1 TB file? By the way, due to the physical structure of the disk, reading the file sequentially is much faster than reading it randomly. Do you think the merge sort algorithm can help with this? Thank you for watching this video. If you like it, please subscribe to our channel and share it with your friends. Appreciate your help. See you next time.